In this video, we're going to discuss basic feasible solutions for polyhedra in standard form. We have already seen the definition of basic solution and of basic feasible solution for general polyhedra, so that of course applies also to polyhedra in standard form. However, we will see how for polyhedra in standard form we can give an equivalent definition which is specialized only for this type of polyhedra. Throughout this video, we will be working with the polyhedron in standard form. We will denote it as usual by P, and as usual, it will be the set of points in Rn that satisfies the system of equalities Ax equal to B and x greater than or equal to 0. The matrix A has m rows and n columns. In order to obtain a nice description of basic solutions for standard form polyhedra, we will make the assumption that all the rows of the matrix A are linearly independent, or equivalently that the rank of A is equal to m. What we will now see is that this assumption can be made without loss of generality. In particular, when our polyhedron P is non-empty, if there is a row of A that is a linear combination of the other rows, then the corresponding constraint can always be discarded because it's implied by the other equality constraints. Here's the formal statement. Let P be our standard form polyhedron and let's assume that it's non-empty. Let's assume that A is an m by n matrix and denote the rows by A1 transpose until AM transpose. Let K be the rank of A and assume that it's strictly smaller than m. Let's define indices I1 until Ik so that K rows that are linearly independent are AI1 transpose until AIK transpose. At this point, let's write down the polyhedron Q defined by non-negativity constraints exactly as in P, but where we only keep our linearly independent equality constraints and we trash all the other one, which means that the equality constraints we're keeping are AI1 transpose X equal to BI1 and so on and so forth until AIK transpose X equal to BIK. Then Q and P are the same polyhedron. I leave the proof of this theorem to you. It's an easy exercise of linear algebra. Note that it's fundamental to use the non-empty assumption. And essentially what you have to do to prove this theorem is to write down every row that you trashed as a linear combination of the rows that you kept. Now the non-emptiness of the polyhedron implies that also the right-hand side of the corresponding equality constraint that you trashed will be the same exact linear combination of the right-hand sides of the equality constraints that you kept. Let's see an example. Here we have a non-empty polyhedron defined by these three equality constraints and non-negativity. Therefore, the corresponding polyhedron is in standard form. Of course, you should check that this system is non-empty, so it has at least one solution. In this example, the matrix A is a 3 by 3 matrix and it has rank 2. In fact, it's simple to see that the second row is linearly independent from the third row and that the first is just the sum of the second and third. Our theorem then tells us that we can just trash the first equality constraint and we're left with a system that is equivalent to the original one. Namely, the set of points that satisfy the new system coincides with the set of points that satisfies the old system. Note that since the left-hand side of the first row is the sum of the second and third left-hand side, also in the right-hand side, 2 is exactly the sum of 1 plus 1, as we expected. And it's clear that this must happen because otherwise you would have an empty polyhedron. A fundamental observation is that whenever you start from a polyhedron in standard form, and as we just discussed, we trashed some equality constraints, then the new polyhedron that you obtain is still in standard form. On top of that, the new constraint matrix will now have fewer rows, so it will now be a k by n submatrix of the original matrix A, and the rank of D by construction will be equal to k. Therefore, we have rewritten our original polyhedron in standard form as a new polyhedron in standard form, where the corresponding equality constraints are all linearly independent. And this concludes the argument that allows us to assume, without loss of generality, that our polyhedron in standard form has all the equality constraints that are linearly independent. Therefore, in the remaining part of this video, we will make this assumption. So let's get back to our original task of giving an equivalent definition of a basic solution to polyhedra in standard form. Once again, we started with a polyhedron in standard form, so given by a system of equality constraints and all the non-negative variables. Our matrix A, as usual, is m by n, and now, finally, we can make the assumption, without loss of generality, that the m rows of the matrix A are linearly independent. In particular, since A has n columns, this means that m is less than or equal to n. Now that we have fixed our setting, let's get back to the definition of basic solution that we saw in the previous video. In particular, we needed to have n linearly independent constraints that are active. Every basic solution, by definition, every basic solution must satisfy all the equality constraints Ax equal to b, and in total there must be n linearly independent constraints that are active. So let's start by looking at the equality constraints Ax equal to b. These are already m active constraints, and they are all linearly independent because of our assumption. And every basic solution will have these m active linearly independent constraints. Now, to obtain a specific basic solution, we need n minus m more active constraints. And the only other constraints that we're left with are the non-negativity constraints, which means that we need to select n minus m variables xi and set them to 0, because setting them to 0 makes the corresponding non-negativity constraint active. However, note that we can't simply choose any n minus m variables xi and set them to 0, because we still have to obtain that the total n active constraints are linearly independent. We're now ready to prove our specialized definition of basic solutions for standard form polyhedra. To do that, let's visualize in matrix form all the active constraints that define a specific basic solution. And we're only gonna visualize the left-hand side of these constraints. We've just discussed how every row of the matrix A forms such an active constraint, and all the rows are linearly independent because of our assumption. So let's write the matrix A here. Now A has m rows and n columns, and below A I want to write the left-hand sides of the other inequalities that are active at a specific basic solution. We have just said that all these constraints have a left hand that is exactly xi for some I. So every such row is a unit vector. Now, up to renaming the variables, I can always assume that these constraints are xi equal to 0 for all the last n minus m variables. So for I that goes from m plus 1 until n. This means that I can write then the identity matrix corresponding to the last n minus m rows and n minus m columns, and 0 everywhere in the remaining block of the last n minus m rows of this big matrix and the first m columns. Now, by definition of basic solution, I know that this big n by n matrix is invertible because all the constraints are linearly independent. But now the structure on the last n minus m rows allows me to write this matrix as a block matrix. Namely, I split A into the first part corresponding to the first m columns that I'm gonna call B, and the remaining n minus m columns that I'm gonna call C. Now this matrix looks like this one. We have B, C, 0, identity, and identity and B are square matrices. Now we just said that this matrix is invertible, which is equivalent to say that it has determinant different from 0. Because this is a block matrix with a 0 in this block, the determinant of this matrix is the determinant of B times the determinant of the identity matrix, which is 1. Therefore, the big matrix is invertible if and only if B is invertible. And the fact that B is invertible can be written in many different ways. For example, I can ask that all the columns of B are linearly independent. So essentially, we have just shown that all the rows of this big matrix are linearly independent, if and only if all the columns of this matrix B are linearly independent. And this gives us the theorem 2.4 above. Consider the constraints ax equal to b and x greater than or equal to 0, and assume that the matrix A, which is an m by n matrix, has linearly independent rows. A vector x in Rn is a basic solution if and only if we have ax equal to b and there exist distinct indices b1 until bm among 1 to n such that the columns ab1, abm of A are linearly independent, and if I is an index different from b1 until bm, then xi equal to 0. In this theorem, the indices b1 until bm exactly correspond to the indices of the columns of B. In our proof, for simplicity, we assume that these were exactly the first m indices, and we restricted to this setting by eventually renaming the variables. In particular, in our argument, when we said that the columns of B must be linearly independent, this is exactly what the point A here says. The columns AB1 until ABM of A are linearly independent. On the other hand, point B says if I is different from B1 until Bm, then xi equal to 0. In our argument, the indices that are not b1 until bm are the last n minus m, and they are exactly those for which I have the constraint xi equal to 0, as written here. So the argument I gave you is just a proof sketch of this theorem, and in particular I made this assumption that b1 until bm are exactly the indices 1 until m, which on the one hand allowed me to give a very clean argument, but on the other hand it's not entirely clear why I can do that. So I encourage you to write down a complete proof of this theorem, and this consists in expanding the argument that I've given you. So overall, theorem 2.4 gives us this equivalent definition of basic solution for standard form polyhedra. While the original definition of basic solution was in terms of linearly independent constraints, therefore of linearly independent rows of our constraint matrix, the new definition still is in terms of linearly independent vectors, but now these vectors are columns of the matrix A instead. Very soon we're going to clarify this theorem through some examples. However, before doing that, I want to stress how this theorem can be used to construct all the basic solutions to a standard form polyhedron, essentially giving us an algorithm to construct all such basic solutions. What you have to do is the following. Among all the columns of A, choose m linearly independent ones, and I'm going to call them AB1 until ABM. For every other index, I'm going to set xi equal to 0, and in order to find all the remaining components of x, xb1 until xbm, I only need to substitute in my system xi equal to 0 for all these i's, and I'm left with a system of m equations in m unknowns. Since the columns of the remaining constraint matrix are all linearly independent, such a system will have a unique solution that will allow us to determine xb1 until xbm. The procedure that we have just discussed allows me to find all the basic solution of a standard form polyhedron. But what if instead I want to find all the basic feasible solutions? At this point, this is straightforward. I can simply construct all the basic solutions, and for each of them, check if they're feasible. The ones among them that are also feasible will be the basic feasible solutions. Let's see our first example. Let's assume that my constraint ax equal to b is this one over here. In this specific example, I have m equal to 4 because I have 4 equality constraints, and n equal to 7 because I have 7 variables. Now we have to choose our indices b1, b2, b3, and b4. Let's choose, for example, b1 equal to 4, b2 equal to 5, b3 equal to 6, and b4 equal to 7. Then I am selecting the 4th, 5th, 6th, and 7th column of A. And in this case, they are all linearly independent. Therefore, I can obtain a basic solution. How can I do that? I set x1, x2, and x3 to 0. This is because 1, 2, and 3 are exactly the indices of the columns that I didn't select, and then I obtain x4, x5, x6, and x7 by solving the remaining system of equations. So once you plug in x1, x2, and x3 equal to 0, I obtain a system that has a unique solution, and in this case it's extremely simple to solve. In fact, the first constraint here will tell me x4 equal to 8, the second will tell me x5 equal to 12, the third x6 equal to 4, and the last one will tell me x7 equal to 6, which is exactly the basic solution written here. Now I can check if this is a basic feasible solution or not. So I only need to check if x is feasible. Of course, it satisfies all the equality constraints by construction, so I only have to check non-negativity. All the components are greater than or equal to 0, so x is a basic feasible solution. What if instead now I change B1 from 4 to 3? In this case, I am selecting the third, fifth, sixth, and seventh column. Again, you can check that they are linearly independent. And now, to obtain the corresponding basic solution, I again set x1, x2, and now x4 to 0, solve the remaining system of equations, and you can check that you obtain x3 equal to 4, x5 equal to minus 12, x6 equal to 4, and x7 equal to 6. Now, this basic solution is not a basic feasible solution because one of the components is strictly negative. Now, the theorem 2.4 that we have just seen will play a fundamental role throughout Chapter 2 and Chapter 3. So what I want to do now is introduce some notation that will allow me to talk about it very easily. The first thing I want to do is give a name to the variables xb1 until xbm. And these will be called the basic variables. All the remaining ones, which are the ones that we set to 0 in our procedure, are called the non-basic variables. Similarly, the indices b1 until bm are called basic indices, while the remaining one will be called the non-basic indices. Again, in a similar fashion, the columns indexed by b1 until bm are called the basic columns. It's important to realize that the basic columns are vectors in Rm, and also, since they are linearly independent, they always form a basis of Rm. Next, I want to define the basis matrix. The basis matrix is simply the matrix obtained by arranging all the basic columns next to each other, so AB1, AB2 until ABM. Such a matrix will always be denoted by capital B. Since all the columns of B are linearly independent, capital B is always invertible. Another notation that I will be using is XB. XB is a vector that contains as its components xb1 until xbm. With this notation in place, I can easily write how to obtain my basic solution. In fact, in my original system ax equal to b, once I've set to 0 all the non-basic variables, I am left with the system bxb equal to b. And such a system we've already seen as a unique solution, but now, thanks to this notation, since B is an invertible matrix, I can directly write its solution as xb equal to B inverse B. This formula is obtained simply by multiplying on the left by the inverse of B. To get familiar with the notation that I just introduced, let's see again our example. Here we chose columns A4, A5, A6, and A7 and obtained this basic feasible solution. So in this example, the basic indices were 4, 5, 6, and 7. Correspondingly, the basic variables are x4, x5, x6, and x7. And the basic columns are A4, A5, A6, and A7. The basis matrix B is obtained by only keeping my selected columns, so in this case I obtain this nice identity matrix, and xb is the vector containing all the basic variables x4, x5, x6, and x7. Now I hope that with this example all these definitions are a bit clearer to you. One thing to be very careful from now on is how to deal with the indices. In fact, many students are confused by these indices b of I. An important feature of these indices is that bi, which is the column I of capital B, is equal to ABI. We can check it immediately in our example. In fact, here we have B1 is the first column of B, while b of 1 in this example was equal to 4 because that's the first chosen column, and so A4 is the fourth column of A, and in fact it's the same column. We have said that the set of basic columns forms a basis of Rm. And it will be important for us in the future to discuss about bases being distinct or different. So let's formally define this here to avoid confusion. So two bases are said to be distinct or different if they involve different sets of basic indices. In particular, what I want to say with this definition is that if two bases involve the same set of indices just in a different order, we will consider them always as the same basis. So let's immediately see an example to understand this, which is a little bit confusing. So let's look again at the same example that we've seen lately. We're just gonna add one more column, which will be exactly equal as the seventh column. Let us now select first the set of columns A3, A5, A6, and A7. And these columns are highlighted here in blue. And then instead, I'm gonna select A3, A5, A6, and A8, which are now selected in the matrix. Now, since I have only exchanged the seventh column with the eighth one, and these two columns were exactly the same, the two sets of columns actually coincide. However, the sets of basic indices is different because in the first we had 3, 5, 6, and 7, and in the second we had 3, 5, 6, and 8. Therefore, following our definition, we have two different bases. In this slide, I want to give you an intuitive geometric view of basic solution. In order to do this, we're gonna get back to our interpretation of the constraints Ax equal to b. If you remember, we wrote it down as the sum of AIxi equal to b, which we interpreted as finding a way to combine the resource vectors AI in order to synthesize the vector b. Now, in a basic solution, we are only allowed to use m of the resource vectors, which are those associated with the basic variables. This is because the non-basic variables are all set to 0. Furthermore, in a basic feasible solution, we have one additional restriction, namely that we can only use non-negative amounts of each basic vector. Let's see an example. In this picture here, we have m equal to 2. How can I understand that? Because I am drawing A1, A2, A3, A4, these are the four columns of my matrix A, and the right-hand side B of my system of equations, and I'm drawing them in the plane. Therefore, each one of them has two components, which means that I originally had only two constraints. The first question that you can ask yourself in this example is which are the bases that yield basic solutions? So a basis will have two vectors among these four, A1, A2, A3, and A4. And basic solutions arise whenever these two selected vectors form a basis of R2. And in this case, as you can see from the picture, any two of them forms a basis. Then you can ask yourself which are the bases that yield basic feasible solutions. The only difference is that in this case, we can only use non-negative amounts of each basic vector. For example, if we select A1 and A3, the question is, can I write B as a non-negative combination of A1 and A3? And from the picture, you can easily see that this is the case. And this happens because geometrically B lies in the cone generated by A1 and A3. On the other hand, you can quickly realize that A2 and A4 do not form a basic feasible solution, because no matter how hard you try, you will never be able to write B as a non-negative combination of A2 and A4. One way to see that is that any non-negative combination of A2 and A4 will have an x2 component that is less than or equal to 0, since both A2 and A4 have a second component that is less than or equal to 0. So you will never be able to obtain b, whose second component is strictly positive. Now I leave it as an exercise to you to figure out all the basic feasible solutions for this example. At this point, I want to stop for a minute to think about the correspondence between basis and basic solutions. From all our discussion, it is clear that a basis uniquely determines a basic solution. We have seen and we've discussed how to obtain such a basic solution, starting from the basis. In fact, we have seen essentially an algorithm that, given a basis, gives us the corresponding basic solution. In particular, this means that if you have two different basic solutions, they must have come from different bases. Now, it would be intuitive to think that also the reverse holds. Namely, it would be intuitive to think that if you have two different bases, then the corresponding two basic solutions are different. However, this is not always the case. In fact, it can happen that two different bases lead to the same basic solution. And I want to give you a very simple example to convince you that this in fact can happen. Just pick any system AX equal to B where B is equal to 0. Then every basis leads to the same basic solution, namely the 0 vector. In fact, once you have set to 0 the non-basic variables, you're left with the system capital B times xb equal to 0. You know that xb equal to 0 is a solution, obviously, and since b is invertible, and since capital B is invertible, this is the unique solution. And so the 0 vector is the corresponding basic solution. This phenomenon will have some important algorithmic implications, and in fact it will make our life harder later on in chapter 3. The last thing I want to discuss in this video are adjacent basic solutions and adjacent bases. We have already seen the definition of adjacent basic solution, and now I want to discuss correspondingly the concept of adjacent basis. As a reminder, two distinct basic solutions are defined to be adjacent if there are n-1 linearly independent constraints that are active at both of them. Now we define the same concept of adjacency but for bases. Of course, this only makes sense for standard form problems because these are the problems for which we define bases in the first place. So two bases are adjacent if they share all but one basic columns. Also here, this definition of adjacency is very similar to the previous one. And again, the main difference in a sense is in the fact that we're looking at columns in common instead of constraints in common. I leave as an exercise for you to show the following connection between adjacency between basic solutions and adjacency between bases. First, adjacent basic solution can always be obtained from two adjacent bases. Second, if two adjacent bases lead to distinct basic solutions, then the latter are adjacent. Essentially, these two conditions tell us that while it can happen that two adjacent bases lead to the same basic solution as we have just discussed, if this doesn't happen, then adjacency behaves as expected, namely that adjacent bases are mapped to adjacent basic solutions, and adjacent basic solutions correspond to adjacent bases. In order to prove these two properties, you can use the same type of techniques that we discussed to prove theorem 2.4. While I'm not going to prove these two properties, I'm going to instead give you some examples. Let's again look at this example where we have our system AX equal to B as written in the slide. Let's first see an example of two bases that are adjacent. Let's pick A4, A5, A6, and A7 and A3, A5, A6, and A7. I only exchange the fourth column with the third. Therefore, by definition, they are adjacent bases. The corresponding basic solutions are x equal to 0, 0, 0, 8, 12, 4, 6 for the first base, and 0, 0, 4, 0, minus 12, 4, 6 for the second base. And these two basic solutions are adjacent. To check that, we should see that they have 6 common linearly independent active constraints. Now, 4 of them come from the equality constraints, and the remaining 2 corresponds to the 2 zero variables that they have in common, namely x1 and x2. So these are the constraints, x1 greater than or equal to 0 and x2 greater than or equal to 0. And this concludes our video on standard form polyhedra. In the next video, we're going to dive into degeneracy.